Hello, everyone. It's really great to be here. I'm so glad to have this opportunity to present our new R package, Crossnma, which can, as Anna said, can do network meta-analysis and network meta-regression in a Bayesian framework. And yeah, I believe there are a lot of potential uses, hopefully, within Cochrane reviews. So this webinar is split into 4 parts. I'm going to talk about the theory behind the development of Crossnma package, namely introduce the 4 Crossnma models. Then I'm going to move on to talk about the implementation of Crossnma and the workflow within its functions. And then Guido Schwarzer will take over, and he will take you through a working example to demonstrate how to use the functions in Crossnma, and end with some limitations and the future plans of Crossnma. So now to the first part of the webinar, I would like to start by defining what we mean by Crossnma model. The Crossnma is a recent extension of the traditional network meta-analysis model that allow for synthesizing data with different formats, and which can come from individual participant data, IPD, or aggregated data, the data you got from the publication. And this data can be collected from randomized clinical trials, RCTs, or non-randomized studies. We have introduced these models, these Crossnma models, in a new article that has been published recently in Research Synthesis Methods. So how we built this model? We started with the 3-level hierarchical model that combines IPD and AD data. And this model has been introduced before by in several articles by Janssen, Saramago, and Donegan. Then we integrate into this 3-level hierarchical model for different approaches to combine RCT and NRS, the naive model that treats RCT and NRS equally without considering any differences between them. And then the bias adjustment models 1 and 2 that accounts for study bias not only on non-randomized studies, but also in randomized clinical trials. And finally, we add the model that runs the analysis for RCT data using priors that are constructed from the analysis with only NRS data. So this integration results in creating the 4 Crossnma models, which serves as a generic framework to allow, again, combining different data formats and different study designs. Now I will give more details about each model. I will start with the description of the 3-level hierarchical model that allow combining IPD and AD. This description is for a binary outcome with logistic transformation, so we estimate odds ratio out of that. Here we have in the first level, we model studies with participant data. So here we assign for the binary outcome Y a Bernoulli distribution with a probability of event to occur B. Then the probabilities are linked to control of treatment effect via a logistic transformation. And here we can adjust the relative treatment effects, deltas, by adding the 3 different for the covariates by adding the 3 different parameters, beta 0, which adjusts for prognostic effect, beta W is the within study treatment covariate interaction at individual level, and beta B quantifies the interaction between the relative treatment effect and the mean covariate across studies. And then for studies with aggregate data, we have access only to summary data. So the number of events is assigned a binomial distribution. Then we have the logistic transformation, where we can adjust only for the mean or the median covariate, because we only access again the summary data. So here we can estimate the between study coefficient beta B. Then we combine the relative treatment effects, deltas, and the between study interaction coefficients, beta B, from both IPD studies and AD studies, while beta W is only combined across IPD studies. So this 3-level hierarchical model can be applied to RCT or NRS data separately. And then to combine RCT and NRS in the same model, we have created different extensions of this three-level hierarchical model. The first one is to analyze both data within the three-level hierarchical model naively by adding randomized clinical trials and non-randomized studies to each level, here to individual and to study level, and combine the evidence without any differentiation between the two designs. Of course, this is not what we recommend to use in practice, but we kind of can use it as an initial step or a base case to compare other analysis to. And as you can see here, we don't acknowledge any study bias, while in the other three Crossnma models, we adjust for study bias in different ways. The bias adjusted model 1 is again another extension of the three-level hierarchical model, which adjusts the relative treatment effects to study bias by either adding the bias effect of each study, gamma 2, multiplied by the bias indicator R. R can take values 0 or 1, and I will give more details about R in the next slide, or by multiplying the relative treatment effect by the bias effect, which is less common case to using the additive bias effect. We do the same for IBD and AD level data, and then we synthesize across the studies all parameters, including the bias effects parameter gamma, using the random effects model, or we can also use the common effects model. Now, about the study bias indicator R, as mentioned before, it takes value 0 or 1 based on a Bernoulli distribution with bias of probability by. So here, if R equals 0, then we don't apply any bias adjustment. If R equals 1, then bias adjustment will be applied. And by the bias probability can be estimated in two different ways. By either assigning a beta distribution, where low risk of bias study is given a distribution that skewed towards 0, and high risk of bias studies provide a distribution that's skewed towards 1, and the studies with unclear risk of bias will be given a uniform distribution. Or instead, we can estimate the bias probability by using study characteristics, for example, allocation concealment using a logistic model. Another way to incorporate study bias in the model is by modeling the bias effect and relative treatment effect simultaneously. Here, we replace the relative treatment effects, deltas by theta. And theta here represents the bias adjusted relative treatment effect. Then these thetas can be combined across studies by assigning a weighted average of two normal distributions. The first normal distribution model unadjusted effect, the D's, and the second model, the second normal model is used to model the bias adjusted treatment, the bias adjusted effect, D's and gammas. The last Crossnma model we have introduced is to combine clinical and observational data is a two-step approach. In the first step, we conduct network meta-analysis or network meta-regression using only non-randomized studies or observational data. Then we get from this analysis the posterior distribution of each relative treatment effects, and then we conduct network meta-analysis or meta-regression for clinical data. And we use in this model the posteriors from the NRS analysis as priors for the basic parameters in the RCT model. Or instead, we can use, instead of the variance of the posterior, we can use the between NRS heterogeneity tau to reflect the heterogeneity between NRS studies. We can reduce the impact of observational studies by either dividing the variance with W, which inflate or increase the variance, and therefore reduce the NRS contribution in the RCT analysis. Or we can shift the mean by zeta, or to adjust for under or overestimation in NRS data. So today I just gave you like a brief introduction about the Crossnma models. There are more details about the models, highlight of the models, limitations, and other options presented in our paper, research synthesis methods. And of course, I couldn't talk about everything because of the sake of the time. So for those who are really interested, I encourage you to go and check the paper. It's open access. So yeah, and now about the implementation of these models in Crossnma. We implemented the different Crossnma models that I talked about in a newer package. We call it Crossnma. We use Bayesian models for parameters estimation using JAX software, and you can use the package not only to run these 4 Crossnma models, but also to run many different analyses using the package, using our package, like network meta-analysis with individual participant data, or the standard network meta-analysis with only aggregate data. You can also decide to include randomized clinical trials, or include only non-randomized studies, or include both of them. Also, you can use it to run network meta-regression. Currently, the package supports up to 3 covariates. In terms of summary measure, currently Crossnma supports using odds ratio, risk ratio, mean difference, and standardized mean difference. And finally, to facilitate the use of the package, we set default to priors following the same approach used in GMTC package and introduced by Wilkenhoff and colleagues. This is the workflow in the Crossnma package. You, as a user, you can begin by providing your own data sets. You can have participant level data set or study level data set, or both of them. Then you call crossnma.model function to produce the JAX model and reformat the data. Then you can display the network of evidence using an netgraph function. Then you can go ahead and run the analysis and estimate all model parameters using the Crossnma function. Then you can display your results in different formats using built-in functions. We have summary, league, and heat plot functions can be used to produce numerical and graphical summaries of the treatment effect estimates. And also you can use the generic functions like plot and summary function to evaluate the Markov chain Monte Carlo convergence. So I think before we proceed to the third part, we can I can take a couple of questions about the theory and the implementation of Crossnma. So
yeah, there are a few questions in the chat. Some have been already answered by Guido.
Okay.
So Katerina asks, can you please explain again what is the beta W in the level 1 of the unadjusted Crossnma model? Why it is involved in 2 parts into the model?
So an unadjusted model. So here, this model.
Yes. So she
Yeah.
asked, what is the beta W?
Yeah, so here beta W is the within study treatment covariate interaction coefficient. So it quantifies again the interaction between the treatment effect and the covariate effect. We split the within study from the between study coefficients because we want to handle the aggregation bias. Yeah, I think that's also here beta W. It's only we can estimate it from the IPD data because we can access participant data, but we can't estimate that from the aggregate data.
Okay. Another question is there any way of joint modeling risk ratios from RCTs and hazard ratios from non-randomized studies?
Sorry, can you repeat the question again?
If there is any way to combine risk ratios from RCTs and hazard ratios from non-randomized studies. So I guess this question is not specific to this model, but in general by your, based on your knowledge.
To be honest, I didn't investigate that in Crossnma.
Okay.
Sorry, I don't have any answer.
Another question is whether the package can handle data from RCTs and non-RCT from aggregate data only without IPD.
Yeah. So you can have any combination of the data.
Okay, and the last question, why to conduct network meta-analysis, or I'm not sure why the package conducts network meta-analysis and meta-regression up to 3 covariates only. So I guess, in other words, is it possible to incorporate more than 3 covariates?
Currently, we just implemented or allowed the user just for 3 covariates. But yeah, if there is, I don't know, in the future, if there is a need for more, maybe we can extend it to more. But in Bayesian models, sometimes it's difficult to manage more covariates. But in principle, you can do it. But currently, the Crossnma just allow for 3 covariates.
Okay. So it's more an implementation issue.
Yeah, just the implementation issue. So yeah, in principle, you can add as many covariates as you like, but you have to check if it's the estimation is possible. I mean, for example, Cochrane recommended for 10 studies to include 1 covariate to be able to estimate the coefficients efficiently. So yeah.